Okay, so we are looking at the bottom of page 4. Today's topic is valence electrons. So valence electrons are really just regular electrons. There's nothing special about what makes them up. If you put two electrons side by side, there would be no differences. But valence electrons are special for one reason, and that is their location within the atom. Their location determines all of the important properties of these electrons. So, valence electrons are in the outermost energy level. So, they are on the very outside of the atom. They are the furthest electrons away. And they're responsible for the chemical behavior. Because they are a part of the outer layer, any electrons that are lost or gained will be valence electrons. These electrons influence the chemical behavior of the atom because when two atoms collide, they are the first electrons to make contact with atoms. Thinking about it in terms of a car, let's imagine you're driving down the road and you accidentally hit a mailbox. The first thing to hit the mailbox, the first thing to get damaged on your car is going to be the paint or maybe one of your side mirrors. So, and that's because they're on the outermost layer of the car. Same thing with the valence electrons. They are on the farthest, the most outer layer, so they're going to be the first ones to touch anything if there's contact. So, if we're going to understand what valence electrons are telling us, we need to know how many they have. So to figure out the number of valence electrons in an atom, we're going to look at the group number. And these are the numbers along the top of your periodic table. And if the top of the periodic table looks something like this, you've got 1, 2, 3, 4, 5, 6, and so on, until all the way over here, we get to 18. If your periodic table does not have group numbers along the top, you might want to write it. These are going to help us figure out how many valence electrons a specific element has. So we're going by the group number. So group 1 is relatively easy. So we're talking about this leftmost group, the alkali metals, has 1 valence electron. Group 1, 1 valence electron. Group 2 has 2 valence electrons. These are the easy ones. So if something has 1 valence electron, that's why it was put in group 1. If something has 2 valence electrons, that's why it was put in group 2. So all of these elements in groups 3 through 12 are transition metals, and we do not work with them in this class very much because they tend to be inconsistent. So skipping those and going on to groups 13 through 18. So what we're going to do is start with the group number and then subtract 10. So for instance, group 13 has 13 minus 10, 3 valence electrons. Group 16 has 16 minus 10, 6 valence electrons. So we'll go through some examples here. The first one that I will look at is the element neon. Neon is a noble gas, which means it belongs to group 18. And because it belongs to group 18, we can figure out the valence electrons. So 18 minus 10 tells us that it has 8 valence electrons. Oxygen is in group number 16. When I want oxygen's valence electrons, 16 minus 10 tells me that it has 6 valence electrons. This one is magnesium. Magnesium is in group 2. Since it's in group 2, it doesn't even require a calculation because we know that anything in group 2 has 2 valence electrons. And it's going to be as simple as that. This element, silicon, is in group 14. To find its valence electrons, group number minus 10 tells me that we have 4 valence electrons here. Potassium, K. Potassium is in group 1, and looking up here, everything in group 1 has 1 valence electron, and that includes potassium. So looking at just a couple more, if we talk about aluminum, aluminum is in group 13. Subtract 10 tells me that we have 3 valence electrons. And bromine, Br. Bromine is in group 17. Subtracting 10 from the group number tells us that we have 7 valence electrons. So the idea of valence electrons transfers pretty well into the next topic, which is the electron dot structure. And the electron dot structure represents an atom. It's a drawing that represents the electrons too. But specifically, it only shows the valence electrons. Only the ones that really make a difference for the chemical behavior. So since these ones are responsible for any chemical behaviors, we can get an idea of the chemical properties. How is this atom going to behave? How does it act? Is it reactive or is it not reactive? And we can get an idea of this without doing a longer electron configuration or orbital diagram or anything like that. So the electron dot structures are especially useful when we're talking about chemical bonds between atoms. As we see in the next few chapters, atoms will tend to gain electrons, lose electrons, or share electrons, all with the goal of becoming more stable. Things in the universe tend to find the most stable configuration possible. So an example of this is I drive to school every day, and as I drive home, I see a couple of barns that are very old. And within the last few years, these barns have they just look unstable. So a couple of years ago, one of these specific barns was standing straight up and it just looked old. And then I noticed over time that it was starting to lean a little bit and lean a little bit more. And then within the last year, this barn found its most stable configuration, which was a pile of lumber on the ground. It just fell over. And it's the same thing with most things in the universe. We are trying to find the most stable way to do things. So, looking at some various elements here. So, neon was the first one last time, so let's talk about neon again. So we need to know its number of valence electrons. And to do that, I look at my periodic table and I find its group number. Remember, its group number is at the top, it's 18. For valence electrons, I subtract 10. So it has 8 valence electrons. Now, when I draw the electron dot structure, I start with the atomic symbol. And the atomic symbol represents the nucleus and all of the electrons that are closer to the nucleus. So this represents the nucleus and everything except the valence electrons. And so I draw my 8 valence electrons, and I start here and I say 1, 2, 3, 4, 5, 6, 7, 8. This is my neon with its 8 valence electrons. And if you'll notice, they are paired up into twos. So it's important down the road. For now, I'll just say it's easier to read it when we do it like this, as opposed to if I just draw it like this. It's harder to see that this one has 8, and it's a little easier to see this one has 8. We also want to avoid something like this where we have, here's the neon and the valence electrons kind of shooting off like this. So both of these are really not good situations. They're just hard to read. If you look at this one, the one that I drew first, if you drew an imaginary circle, all of my electrons, all of the valence electrons are more or less on this circle. So then my next element, let's look at oxygen. And oxygen belongs to group 16. So to find its valence electrons, we subtract 10. It tells me that oxygen should have 6 valence electrons. So I start with the atomic symbol, and this represents the nucleus and all of the inner electrons. And then I draw my 6 valence electrons. There's my 6 valence electrons. So a few more. Nitrogen, we find it in group 15, which means it has 5 valence electrons. Here's my nitrogen, 1, 2, 3, 4, 5. A few others. Here's SR, strontium. And strontium belongs to group 2, which means we don't need to do a calculation. We don't need to subtract 10. All we need to do is find the group number, and that is the valence electrons. So here's my strontium. This represents the nucleus and the first 36 electrons. And the only ones that I care about are these two on the outside. Here's sodium, Na. It's in group 1. It's an alkali metal. So everything in group 1 has 1 valence electron. And Here is my sodium with its 1 valence electron. This electron is important. So the 10 electrons that are here don't really do a whole lot. They do something, but not that interesting. This one is the one that's really interesting. This electron does not like to hang around with the sodium, and it does all it can to react with other chemicals and just go somewhere else. So with this sodium, this electron will react with water, and it'll break the water into a couple of different pieces. It lets off hydrogen gas, and it makes this sodium more stable. Something that you'll see in a demonstration at some point in the class. Here's another one, and this is arsenic. We find it in group 15, which means it has 5 valence electrons. And so here is my nucleus and all of the inner electrons, and here are my 5 in the outer layer. Iodine. So iodine, we look up and we find it towards the bottom of group 17. That means it has 7 valence electrons. And here are my 7 valence electrons and my electron dot structure.